I am here at the lab here at the University of Houston, Victoria, where I do conduct some of my research. And I'm also representing the Morningbird Foundation and the research that we undertake there, which supports our STEM education and research initiatives. And that is the primary function and mission of the Morningbird Foundation. And you can learn more about that on the website, morningbirdfoundation.org. But what I want to discuss today is really working towards an experimental verification of space-time distortion, of being able to do it ourselves in a laboratory under controlled settings in order to begin to build a pathway towards warping space-time and perhaps even superluminal travel, propulsion, which is kind of, I guess, the holy grail. And this is how we will lay out the presentation. I'll give you the rationale, which you probably are all very much familiar with. Then the background, the approach I'm taking, modeling and simulation of that approach, the experimental approach, and then some of the implications of what it would mean should we be successful. And finally, just some of the collaboration that I've been involved with so far, and also just letting you know that I'm looking for further collaboration. So if some things that I talk about, say here, spark some ideas and perhaps potential collaboration, I would be more than happy to hear from you and work with you, and I'll let you know how to connect with me once we're all done. Okay, so as I said, many of you know most of this. Our current space travel capabilities has its limitations. Right now, probably the fastest known man-made object is that NASA solar probe, clocking at about 531,000 kilometers per hour. And there are different missions that we're trying to undertake that just within the solar system that are just daunting to think about when you really start looking at the potential distances involved and the speeds required, because one of the issues with the speed, obviously, is that you have to accelerate up to those speeds, and there's a limitation to the amount of acceleration a human body. So if we're talking about human travel limitations, and in addition, kind of our cosmic speed limit at the and I know some of that is a little bit controversial, but the speed of light kind of being the fastest speed that physical matter can move within real space-time. Now, just giving you an idea, you've seen these before where you kind of move outward and you see just how far we're talking about. So you had 10 billion kilometers looking at our major part of our solar system. As you go out to finally 1 light year, we're just outside of our solar system to the Oort cloud. As you get further, 10 light years, this is where you see our nearest stars, our neighboring stars. You see the Alpha Centauri, Sirius, those stars that, if we were going to try to travel to other star systems, these would be candidates. And you can see just how far just 10 light years would be. If you could travel at the speed of light, it would take you 10 years to get there. Under our current propulsion, it's unthinkable. The Milky Way galaxy where we live, a little bit more than 100,000 light years across. So being able to move about our galaxy, we would have to be able to travel at speeds in excess of the speed of light. So in any case, and finally, the universe itself, at least well known. There's billions of light years that you would need to traverse such distances if you want to travel about the universe. Now, this is where the background of all of this comes. And Alcubierre developed this metric, and this is a particular solution or particular metric that he put forward that suppose that if you could bend space-time, and the graphic you see at the top left, it's been kind of popularized because it looks nice, but it gives you kind of an idea. But when you see this part going down, that actually means that space-time is being compressed, and in the back of the vessel, the space-time is being stretched. If you were to do that, and that's what this metric supposes, then you would be able to move a vessel forward. And it even suggests that with enough energy, you could even travel faster than light. Another good analogy to think of is that if you were sitting in your car and you want to travel down the road, normally you press the accelerator, the car starts moving. But instead, what if the whole road and everything around it was moving and the car was standing still? You would get to your destination, but you would not feel the inertial effects because everything else is moving around you. This is kind of the idea. All right, so and that's what I have in this slide, just to give you that picture. Now, here is the particular shaping function. If I go back to the metric, this f of r is the shaping function that Alcubierre suggested. This is the mathematical equation here, and this is what it would look like visually as you go out in radius. And the York time measure that falls out of it is directly proportional to the derivative of the shaping function with respect to the radius. And that's where you see that this, again, this kind of negative means you're compressing space-time, and this positive means that you are stretching it. The vessel is here within this flat or relatively flat space-time that the vessel would reside. So if you could move much faster than light, I'll just give you some examples here of what would happen if you would want to just travel around the world by a method that you were at 0.5 C. You could get around the world in less than a second. And here's other things. See the nearest star, if you could move at 10 times the speed of light, you could get there in about 5 months, which is a reasonable time for a human space travel. But it's one thing to say all of this, it's another thing to try to actually do it. And this is a little bit better depiction of what happens. First of all, you see that, space-time is compressed here, is stretched behind. Inside is probably the most significant part of the vessel. But the thing I wanted to also make it clear is that whatever you're doing to stretch and compress space-time is contained within your bubble, but your material, some have proposed this, some of this should utilize your exotic material that some have suggested, but it all has to be contained within that, not some of the other visual that we showed kind of implied that the space-time, that the vessels, those round appendages around the vessels are what causes the space-time to distort, but it's outside of that, but it should be inside of your material and everything. And I'll be a little more descriptive in a second. Okay, but here's the problem. Here's the problem. In order to do this, there was a energy density requirement calculated by Alcubierre. And in that solution, not only was the energy density requirement enormous, but also it was negative. And while some researchers are mentioned here worked to reduce the magnitude of the energy density requirement, the polarity of it, if you will, was still negative, and that was an issue because no one really knows what negative energy is. I know there's been some speculation around Casimir effect, for example. Some have suggested some sort of exotic material that would lead you to there. Antimatter, all these different approaches to try to overcome this. So this is the drops out of Einstein's equations, and this is the energy density expression that comes from the Alcubierre metric. And as you can see, there's a big giant negative sign right here. All of these terms are squared, so it doesn't seem that there's a way to turn that negative sign positive till I looked at this. Now, my background's in electrical engineering, and I played around with complex numbers and all that, and know that if you have an imaginary number and you square it, then it becomes negative. And then if you multiply the negative with the negative, now you can turn this equation positive. So what I was looking at was what would it take to do that, and with the shaping function, because that's something that you could have control over. These other things you don't have as much control over. So the shaping function, if we had a value of it that has a imaginary component that is greater than the real component, then when you square it, it becomes negative, and then this energy density becomes positive. So that's the mathematical basis of what I was coming after this with, and this kind of just walks through that. And in a simulation of that, you see now the energy density, which before was negative and pointing downward, now is positive for the right values. Now, it's one thing, again, is mathematical, but I began to sort of say, is there anything practical that could be derived out of this? And so I began looking at materials, because again, as an RF engineer, had familiarity with dielectrics and their interactions with RF as an electromagnetic wave passes through a dielectric material, what happens. And so I began looking in that space, and again, to essentially try to find a dielectric material that has a property of a complex, having a complex dielectric constant, relative dielectric constant. And lo and behold, I was able to find one. It's something called ethylene glycol. And you're probably very familiar with it because it is essentially a coolant or an antifreeze, but at the right temperatures and at the right frequencies, it has a relative dielectric constant where the imaginary part is greater than the real part. Now, RF engineers don't like this, because if you're trying to send a signal through a material, you don't want it to be absorbed. And this is what's called a lossy material. But if you think about it in another way, it's storing up energy. And what is it doing with that energy, and how's it being dissipated? And so then I began looking at the molecules themselves. Now, it looks like I'm not able to actually play this video, but in the other slide there's a link to a video that kind of shows what happens to this ethylene glycol molecule as the energy is applied to it. And what you'll see is that there are variations or twists and turns instead of just in most lattices where the energy is passed through, then the phonons, cause energy to pass through and it just vibrates back and forth. In this, there are twists and turns that happen. And I think that is where the complex dielectric constant comes from, because these numbers, for example, are developed from the Debye model, and it is modeled as having that particular value, and you'll get this rotational type of movement as well as that back and forward. Now, again, I'm just going to speculate, and this is speculate and even not even a hypothesis, I would say. But if the molecules themselves are connected to space-time, then perhaps the twisting and turning and tugging on space-time itself, it could allow some distortion to happen in a material like that with the right frequency and with the right temperature. And that's the speculation. This is, the permittivity of a dielectric material. As you can see, the relative permittivity being like this. And it just kind of showing the same thing I showed before, that if you square that, now you have a value that the real part will be less than 0, and therefore multiply and make the overall energy density if you use it. Now, this is what I was getting at. So you have an energy that is, well, in this case, an electric field that enters into a material, and with real dielectric constant, you'll have the electric field exit. It may be smaller in magnitude, but it does, exit without much distortion. In this case, and again, with it being lossy, you do have this rotational action of the molecules that happens, and the new electric field is much less than that which was initially put into the material, and therefore that's where you get the lossy behavior. Now, that's why RF engineers and others just kind of, and those who work with light as well, just kind of avoid this type of material, because you lose the energy that you put in. Now, just to kind of take it forward, I mentioned that the numbers that you saw in the table were developed from a Debye model. So I wanted to do some measurements. And one of the things I did, I made a slight modification to the material by adding a gelatin, because the ethylene glycol is a liquid, it's a clear liquid. And I made a gelatin just so that it would fit within the chamber I was developing a little bit without leaking out and all that. But I did change the properties. Excuse me, I'm trying to get my lighting back. Give me 1 second. Sorry about that. I'm in a lab that has time lighting and I can't do anything about it at the moment. Okay, but it has this we actually sent this down to the University of South Florida, had them do dielectric measurements. Now, what you'll see is that essentially the behavior that we were looking for got pushed out to beyond 4.5 gigahertz. So right around almost 5 gigahertz, you start to see the imaginary part, the real part being greater than the imaginary part being greater than the real part. That's the blue line is the imaginary part, and the red line is the real part. So that behavior happens out here. I'm having them measure the pure liquid. I don't have that data yet, but I expect it to be back here. But I wanted to see whether this gelatin would work the same way. But I do see, you see the kind of the modifications to the values. All right, but so what I'm looking to do is to create a cylindrical resonant cavity filled with this material, and then excited with an electric field in the TM010 mode at around 2.5 gigahertz. And so we would have this type of distribution of the field, which essentially is almost like a half cosine. But in any case, this is the distribution of the field. So you'll see that it has a distribution that has a differential across with respect to the radius. So therefore, you can get some change, and that's what you need, is some change. df/dr has to not be zero in order for there to be some action that or hopefully we'll see. So this is what it would look like instead of this top hat hyperbolic tangent type of shaping function that Alcubierre put forward. Now, so in this case, this is what the shaping function would be from the center outward, and then if you do analysis of the energy density and the York time, you would have to kind of look at York time by turning this graph in probably 190 degrees. But as you can see here, the energy density that you're expecting is similar to what you saw with in Alcubierre's work. So we're just trying to again get some change there, but the important part of it is that it is positive. Those are positive values for the energy density. The York time model kind of looks like this for it. It doesn't have that flat center. Now, look, this is not something that we're trying to put a ship in and start propelling things. What I'm trying to do is just show that we can experimentally distort space-time under the right conditions, and then it gives us something to work with. And I just want to detect that space-time has been distorted at some level within the chamber. That's my goal. And having shown that, then you can start to take it to other levels of determining use cases and things of that nature. Now, so within the chamber, in order to do some more analysis here, you want to calculate the energy density within the chamber due to the RF, and then equate that to the energy density in order to, given by the Einstein's equations, in order to try to come up with an expression for what distortions we would see versus how much input power we would apply. That's what this is. And so the calculation to determine the power density inside, then by equating it to the energy density, we're calculating the energy density inside due to the input power, equating it to the energy density due to Alcubierre's work. And this is what you get. And this is essentially an expression of the maximum input power versus how much distortion, that's what delta X is, that you would see. Now, as you might expect, the power levels are very high if you want to get any reasonable distortion. But what I want to find out is what a measurable distortion. And in a few minutes, I'll make the case that nanometers are indeed measurable. And if I can get distortion on the order of just nanometers, I would only need, as you can see here, roughly 10 watts would give you just over, let's just say that's about 30 nanometers of displacement and so on. And you could get a little bit less back here. And as you can go up in power, you could get a little bit more. Now, of course, given the physical experiment that we're looking at, you know, there be some limitations on just how much power the chamber itself could stand. But again, I want to be able to detect nanometers of movement, and then we could make our experiments more and more sophisticated. So I have this, some of you probably familiar with COMSOL. It's a pretty comprehensive simulation package, and I'm using that to model this chamber, which I'll show you what it looks like in a second, and to measure what happens with the fields within the chamber. You could also measure things like temperature and pressure as well, and model and simulate that. So I'm working on that, which, you know, as you know, it allows you to do this pretty detailed analysis if you're pretty familiar with it. This is what one looks like. I've actually fabricated. Matter of fact, I'll just go and pick this up. This is the chamber and the fixture. Now, what you see is a hole through the center, and I'll describe what that is in a minute. But what this basically does is RF is pumped into it through here. This is approximately, you know, the right size given the material inside and the frequency that of interest, and then it's set up to work within an interferometer, which this is the experimental approach that I want to describe to you. So if many of you are familiar with the interferometer, you probably know that gravitational waves are being detected using a large interferometer, the LIGO experiment. So think of it like that. But what happens is that if space-time is distorted in any way, then its path is disrupted. And if you can disrupt its path, then you can detect it with an interferometer. So I have a 532 nanometer laser sitting right over there. And this laser goes through, it's split at the beam splitter, bounces off the mirror here, comes back, goes through the hole in the chamber. So I have to, you know, really set this and establish this in the right position, which I took it out. So now I'm going to have to go back and do it again. But such that the beam goes through, bounces off the mirror, comes back through that hole, and comes to the splitter, combines here, and that's where you'll see the interference fringes. Now, I have a 2.5 gigahertz source, amplifier, and for now, currently, I'm trying to get my amplifier to work to give me about 10 watts. But as I've been talking to some here, I might be able to get something a little bit better. Here's a key point, and I want to focus on this. This pulse generator, I'm going to pulse the power. Reason I want to do that is, number one, I want to be able to make sure that any other extraneous movement, noise, and other things are not impacting that. That's not what we're reading. So if I'm pulsing this power at the right levels, at the right rate, pulse rate, and duty cycles and all that, I'll be able to detect whether it is my actions or the actions of the signal the RF that is creating the distortions that are picked up at the screen here. I will be able to determine that versus some other action that might be happening, because essentially you can stomp your feet or bang the table or whatever, you'll see movement on the interferometer. So it's very, very sensitive measurement. So I want to make sure you're eliminating other type of interference. But this is the experiment diagram of what we're going to be doing. And it gives you these type of fringes. I have some better pictures, but this is essentially what you're looking at. The 532 nanometer laser is green, but this is the setup, and this is where you see it. And I showed you the picture earlier where the chamber actually was sitting in between here, and tuned just so that the beam goes back and forward through it. Now, so just a simple way of measuring it was basically shining a camera at the interference fringes that you see on the screen. And this picture up here is what it looks like. And I just did a test of just moving the mirror around here. And as I measured a frame to frame error at 30 frames per second, you see that if there's changes going on, then you would actually see this picked up. So my hope is that as I'm pulsing the chamber with the RF at the right rate, you'll see distortions happen at that same pulse rate and on the order of what we're looking at. And if it does happen, then I'll know experimentally that we caused it. So we intend to show this process by which we can experimentally distort space-time in a controlled environment in a repeatable fashion, and that's going to be key. So once we know we can do this, you should be able to replicate it in your labs. I want to show that a combination of materials and the geometry and the input power has a potential to do this in the desired fashion. Now, a point I'd kind of skated over, and I want to come back and just make sure it's clear that we're also looking at metamaterials as a way to do this, and being able to design metamaterials that have these kind of complex dielectric characteristics, and then do that, because it could be easier to work with in some sort of liquid or gel or some other material. So that's the approach that I'm trying to take in order to do that. I'm supposing that this kind of tugging of is happening at the molecular level, this tugging on space-time. That's the action that is happening, and that's what the energy is doing, is tugging on these molecules, which is therefore tugging on space-time, which is causing the distortions. And that's why the complex material does it, because it has this rotational motion versus just straightforward phonons within the lattice. And again, kind of backing up to the equations that Alcubierre put forward, that's why I believe that the complex number inside that square term is what makes the energy density requirement positive. It's using the energy to do the things that I'm talking about. So that's again my hypothesis, and we're going to probably be arguing over that for years to come. Now, controlled space-time distortions not only have implications for propulsion, but also containing reaction, manipulating energy, shaping fields, a lot of different things. And I've been working with some people who are looking at it for a particular purpose. And we want to see if this method is a way to do it. And we're looking at some other methods also. And then we'll learn more about energy and material requirements that we need to carry out space-time distortion and manipulation by taking this approach. So could we scale this up to something that would allow a ship to be propelled through the far reaches of space at faster than light speeds? Perhaps. But we've got to show that we can do it first at the smallest of level. Now, we know that all matter and energy manipulate space-time. Everything has a gravitational field, in virtue of E equals mc squared. It goes back and forth. It's energy matter duality. We just have to figure out how to utilize it in a repeatable fashion, in a way that we can begin to exploit it. And that's just the approach I'm trying to take. This is just my background. I mentioned the Morning Bird Foundation. That's what I do there. This is the connections that I've been building over the years through some of the universities I've worked with, as well as these organizations that I work with. And this is just some of the imagery that kind of shows that I've been doing that. There's the NASA meeting. This is at NASA headquarters in the Marshall Space Flight Center headquarters in Huntsville. This is at Johns Hopkins. These are some of the deans of engineering from the different HBCUs and MSIs around the country. This is Dr. Sonny White and I at his place, Limitless Space. This is Greg Hodgkin at ZC Institute. I said is working together with a team of people looking at some very interesting things, and I'll let him talk more about it when he gets the chance, if he so chooses. This is work at SpaceX that I do and continuously do. So, and just to summarize, this is just to establish a framework for controlled experimental distortion of space-time. That's what I'm trying to accomplish. I want to show definitively that a complex dielectric material having the right values is what can make this happen, and where perhaps a non-exotic material, unless you want to call this an exotic material, but this is what allows you to be able to do it. Then we've derived this experiment using this Michelson interferometer, which will provide the resolution necessary to detect a small distortion. And we intend to work with others, and I'm looking forward to doing that, working with others to improve all of these different aspects in order to try to make this happen. And I'm looking forward to that. This is just some of the references, and these slides they can be made available to however you want to do that. And so let me just finally say a couple of things. One is that as I said, I'm looking forward to working with people. I'm looking forward to hearing your thoughts on our approach. If there are others doing something similar or in a different way, I'd love to hear that, because I think that if we're going to do this, whether you're interested in traveling at superluminal speeds or anti-gravity or whatever, other utilizing energy and things like that, if we're going to do all that, we have to collaborate, but in ways without fear of this is my idea, this is your idea, and all that stuff that happens. But I'm looking forward to working with people. The other thing is that one technical point I want to make clear again with this chamber is I'm trying to get just movement of distortion within the chamber, And what I think what happens with the mathematics is that, people have gotten used to just plugging a velocity into that expression, say, all right, if I want to go this fast, I plug the velocity in, that tells me how much energy I need. But it is the shape of the space-time distortions that allow for movement, and the movement in relation to time is what gives you the velocity. So if you don't compress in one side and stretch on the other side, and you do something else, then you won't move. So for example, if you compressed on both sides, you won't move, but you'll still be distorting space-time. And you may want to do that for some reason. So, you would still have to put in a certain amount of energy in there to do that, but you won't be zipping off, into the cosmos. So, I just want to make sure that it's understood that the shaping function and what you're actually doing to space-time is what determines the velocities that you propel or don't propel, or whatever it is you're actually trying to do. Because you may be able to formulate small wormholes or rip space-time if you put too much energy in, or some other thing that you might want to do. Thinking about the shape of the shaping function, what you're doing to space-time, that's how we should be engineering the uses that we're starting to speculate about. So I just wanted to make that point at the end. But with that, looks like I'm ending up a little bit early, but that's all I have to say on it. And I don't know if you're having questions or how you might be going about it, but I'll end it right here, Tim.